Good morning, good afternoon, and good evening to everyone who joins us from around the world.
We're so glad you're here.
This is Andrew and Renee. Welcome to the Stack series.
Yes.
Today we are exploring entropy.
Which is a massive topic.
It really is. And I have to admit, when I saw this topic on the docket for our exploration today, I had a bit of a flashback.
Oh, yeah.
Yeah. It took me right back to my college days. Specifically, the dorm room.
Oh, no. I know where this is going.
You know the exact one? The inevitable, unstoppable slide from, I just organized this desk perfectly to I literally cannot find my keys under this mountain of pizza boxes.
It is the classic visual, the messy room. I mean, it's the analogy that launched 1,000 high school physics lectures.
Exactly. And usually that's where the conversation completely stops. We just say, entropy is disorder, we shrug, we clean our rooms, and we move on.
Right.
But looking through the research you've pulled together for our deep exploration today, I get the feeling that messiness doesn't even scratch the surface.
It doesn't just scratch the surface. It might actually be leading us down the entirely wrong path if we stop there.
Really?
Yeah. I mean, the messy room is a useful metaphor, sure, but it's dangerously incomplete. If we settle for entropy is just clutter, we miss the much bigger, much stranger picture of what's actually happening in the universe.
Stranger how?
Well, we miss the fact that this single concept is the golden thread connecting, the steam engines of the Victorian Industrial Revolution to the way our DNA codes life, to the digital revolution of the 20th century, and all the way to the event horizons of black holes.
That is, steam engines to black holes?
And everything in between. It's not just about a messy desk. It's about the fundamental nature of time, information, and reality itself. It is a journey from the very large to the very small, and eventually to the very weird.
Okay, that is a massive claim.
I know, but the sources back it up completely.
So the mission for today is to figure out what this thread actually is, to move past that simple disorder label and understand what entropy really means.
Precisely. And if we do our job right, by the end of this hour, you might stop seeing entropy as just chaos and start seeing it as a measure of what we don't know.
What we don't know.
Yes, it is the quantification of our ignorance.
I love that phrase, the quantification of ignorance. All right, let's get into it. And I assume if we are going to understand this properly, we can't exactly start with black holes.
No, definitely
We
not.
have to go back to the beginning.
We do. And the beginning isn't the Big Bang, surprisingly. The beginning of our understanding of entropy is actually much grittier. We need to go back to the 19th century.
The Industrial Revolution.
Exactly. We are diving into part 1, foundations, what we think we know.
Okay, set the scene for me. We are talking what? Top hats, cobblestones, and coal smoke.
Lots and lots of coal smoke. Picture London or Manchester in the 1850s. The world is changing incredibly rapidly.
Right.
We are moving away from muscle power, horses and humans, to machine power. The steam engine is the absolute king of the world right now.
It's everywhere.
It is pumping water out of mines. It is driving locomotives across continents. It is powering the massive textile factories.
But these engines weren't exactly high-tech by our modern standards, were they?
Not at all. They were beasts. They were loud. They were dangerous. And critically, they were incredibly inefficient.
Inefficient in what way?
Well, you would shovel literal tons of coal into the furnace, right, creating massive amounts of heat. But only a tiny fraction of that energy actually turned into useful work.
But useful work, you mean turning a wheel or lifting a weight?
Exactly, moving the train forward. Most of the heat just radiated out into the room or went up the smokestack.
Right. And in that environment, efficiency isn't just an academic physics problem. It's pure money.
Exactly. If you are a factory owner, every piece of coal you burn that doesn't do work is literally money vanishing into the air.
So there was a huge financial incentive to figure this out.
A massive incentive. There was this intense scientific race to understand heat. What actually is it? How does it move? And how do we get the most work out of it?
And into this race steps a German physicist, right? Rudolf Clausius.
Yes, Rudolf Clausius. And he is the one who spots the fundamental problem.
What did he see that others missed?
He spotted an asymmetry in nature. Now, at this point, scientists were starting to solidify their understanding of the first law of thermodynamics.
That's the one most people know from high school. Energy is conserved.
Right. It isn't created or destroyed, it just changes form.
So the chemical energy in the coal turns into heat energy in the boiler, which turns into kinetic energy in the train wheels. The total amount on the universal ledger sheet stays exactly the same.
That is the first law. And in a perfect theoretical world, you could just swap those energy forms back and forth forever with zero penalty.
But Clausius noticed a penalty.
He did. He noticed that while the quantity of energy stays the same, the quality of that energy changes.
Quality. What does it mean for energy to have quality?
Think about it this way. It is very, very easy to turn work into heat.
Okay.
If you rub your hands together right now, what happens?
They're warm. Friction.
Simple. 100% of your physical movement can essentially become heat. But now, try to do the exact reverse.
The reverse.
Can you take the heat from your warm hands, gather it up, and turn it back into the physical movement of rubbing them together?
No. That heat just drifts away. It dissipates into the air in the room.
It dissipates. And that is exactly what Clausius realized. You can never get 100% efficiency when turning heat into work. Nature always charges a tax.
A heat tax.
Every single time you run that steam engine, some of the energy becomes unusable. It spreads out, it degrades.
So the energy is still in the universe. It hasn't disappeared, but it's locked away. It's retired.
That's a brilliant way to put it. It's retired. It can no longer be hired to do a job.
Wow.
And Clausius needed a way to mathematically measure this unusable content, so he coined the word entropy.
Where does that word come from?
It comes from the Greek word for transformation. He defined it as a measure of the energy in a system that is no longer available to do useful work.
And his big world-changing discovery was that this entropy never goes down.
Never. In a closed system, entropy always tends to increase. It never decreases. This is the second law of thermodynamics.
The second law.
Yes. Things tend to level out. Heat flows from a hot object to a cold object. It never, ever flows from cold to hot on its own. You can't unscramble an egg.
This brings up the arrow of time concept, doesn't it? Because this is always fascinating to me in the source materials. Most physics equations, they don't actually care about time.
You are totally right. Look at Newton's laws of motion. If I show you a video of a planet orbiting a star or billiard balls bouncing off each other on a table, and then I play that exact video in reverse.
It still looks like normal physics. It doesn't look wrong.
Exactly. The laws are time reversible. The math works perfectly in both directions. But now, imagine a video of a campfire.
Okay.
You see the wood turning into ash, the flames flickering, and the smoke rising up into the sky.
Totally normal.
Now, play that video backward. The smoke rushes down out of the sky into the fire. The ash magically assembles itself back into a solid log of wood, and the heat sucks itself out of the air.
That looks like magic. It looks completely impossible.
Because it violates the second law. The second law is the only fundamental physical law that distinguishes the past from the future.
Because it dictates a direction.
Exactly. It tells us that the future is the direction where entropy is higher. That is the arrow of time.
So if entropy didn't exist, time, or at least our human experience of before and after, wouldn't exist.
In a strict thermodynamic sense, yes. We know the past is fixed and the future is open specifically because we are constantly moving from a state of low entropy to high entropy.
Okay, so Clausius gives us the big picture. We've got steam engines, heat flow, the inevitable slide into uselessness. But I feel like we're still stuck in that macroscopic world. We're looking at big tanks of water and fire.
We are.
How do we get to modern understanding? Because entropy isn't just about steam engines anymore.
To do that, we have to zoom way, way in. We have to go from the massive iron engine down to the microscopic atom. And we have to talk about a man named Ludwig Boltzmann.
Ah, Boltzmann. The source had described him as a tragic genius. Why tragic?
Because he was absolutely right, and almost no one in his time believed him.
Really?
You have to remember the context. In the late 19th century, atoms were not a settled scientific fact.
That is wild to me. I just assumed by the late 1800s, with all the chemistry happening, we were completely sold on atoms.
Not at all. Many prominent scientists, they were called the energeticists, thought atoms were just a convenient mathematical fiction, a trick to make the math work. They didn't think they were real, physical, bouncing objects.
But Boltzmann did.
Boltzmann spent his entire life fighting for the idea that matter was made of discrete, real particles. And he deeply believed that if you wanted to truly understand heat and entropy, you had to look at what those individual particles were doing.
So Clausius is looking at the big cloud of steam. Boltzmann wants to look at the individual molecules of water inside that steam.
Exactly. And this is where we have to slow down and really get our heads around his insight because it changes everything about how we view the universe.
Yep.
Boltzmann introduced a field called statistical mechanics.
Which I have to say sounds terrifying.
It sounds like terrible math, I know, but the core concept is actually beautiful. He said, look, we can't possibly track every single bouncing atom in a box of gas. There are trillions of them. It's impossible.
Right.
But we can look at the statistics of how they behave together. To do this, he introduced two vital concepts, the macrostate and the microstate.
Okay, walk me through those. Break them down.
Okay. The macrostate is the big picture. It's the stuff you can measure from the outside with a normal instrument. Temperature, pressure, volume.
Like saying the water in this glass is 80 degrees.
Exactly. 80-degree water is a macrostate.
Got it. The overview.
The microstate, on the other hand, is the exact, specific arrangement of every single atom inside that water. Atom A is right here moving at this exact speed. Atom B is over there moving at that exact speed, and so on.
So for any given macrostate, like our glass of hot water, there must be just trillions of possible microstates that add up to that same temperature.
Trillions upon trillions upon trillions. It's an unfathomable number. Now, here is the analogy that I think works best to explain this. Let's forget the messy teenager's room for a second.
Okay, thrown at the pizza boxes.
Imagine a standard deck of cards.
Okay, 52 cards.
If you go to the store and buy a brand new deck, open the plastic, how does it come out of the box?
It's perfectly ordered. You've got the ace of spades on top, then the king, queen, jack, all the way down. The suits are all grouped together.
Right. That perfect sequence is a very specific macrostate. Let's call it ordered.
Okay.
Now, how many specific arrangements, how many microstates result in that exact perfect order?
Just one. I mean,
Sure.
if you swap even a single card, if you switch the 2 of clubs with the 3 of clubs, it's not in perfect order anymore.
Exactly. Just one single microstate. This is the definition of low entropy. It is highly unique. It is incredibly specific.
Okay? I'm with you.
Now, take that deck and shuffle it. Just give it a good, messy shuffle for a minute or two. What do you have now?
A mess. A completely random sequence of cards.
Let's call that a disordered macrostate. But here is the critical question Boltzmann would ask you. Is the specific sequence of cards you are holding in your hand right now, let's say it's the 3 of hearts, followed by the jack of diamonds, followed by the 7 of clubs, and so on, is that specific sequence rare?
Well, I mean, statistically, that exact random sequence is just as rare as the perfectly ordered sequence, isn't it? Any specific order of 52 cards is 1 out of,
Yeah.
what is the math, 52 factorial?
Yes, which is a massive number starting with an 8 and followed by 67 zeros.
Right, so every specific microstate, whether it looks neat or messy to my eyes, is equally unlikely to happen.
That is the crucial point. But how many of those 67 zero microstates look ordered to you?
Basically none of them. Maybe a tiny handful where a few of the suits accidentally stick together.
And how many of them look disordered or random?
All the rest of them. The other 8 point whatever bazillion of them.
That is Boltzmann's absolute genius. The reason the deck gets disordered when you shuffle it isn't because the universe hates order.
It's not a mysterious decaying force.
No, it isn't because there is a physical force pushing the cards apart. It is simply because there are vastly, overwhelmingly more ways to be disordered than there are ways to be ordered.
It's literally just a numbers game.
It is pure probability. If you start in a state with only one microstate or ordered deck and you randomly move around by shuffling, you are statistically guaranteed to move into a state with billions of microstates.
Because that's where all the options are.
Exactly. Not because you were forced to, but because it is wildly, unimaginably improbable that you won't.
So when my hot coffee cools down on my desk, it's just the universe shuffling the deck.
Yes. There are very few ways for all the fast-moving, energetic, hot atoms to be perfectly clumped together in your ceramic cup while the rest of the room is cold.
That's a low probability state.
But there are infinite ways for those fast atoms to bump into the air and spread their energy out into the room, so they spread.
Because it's statistically inevitable.
Yeah.
That really makes entropy feel less like a force of destruction and more like just the inevitable math of large numbers.
That is exactly what it is. And Boltzmann mathematically proved this. He gave us the definitive formula. Literally, it is carved on his tombstone in Vienna.
What's the formula?
S equals K log W.
Okay, let's decode that for a second. S is entropy.
Yes, S stands for entropy.
And K.
K is Boltzmann's constant. It's really just a tiny number to make the microscopic units line up with our macroscopic human measurements.
And the W.
W is the magic letter. W is the number of microstates, the total number of ways the system can be arranged internally while still looking the same from the outside.
So if W is 1,
Mm.
like our perfect, pristine deck of cards,
Yeah.
the log of 1 is 0. So the entropy, S, is 0.
Correct. Perfect order means 0 entropy.
And if W is a huge number like our shuffled deck, the entropy is very high.
Precisely. High entropy means high probability. It means the system is in a state that is very easy to be in simply because there are so many different ways to be there.
It's incredibly elegant.
Yeah.
But you said he was a tragic figure. It's tragic that he faced so much pushback for something so mathematically sound.
It was hugely controversial at the time because it reduced the rigid laws of the universe to gambling. It replaced absolute certainty with likelihood. And sadly, the constant rejection took a toll. Boltzmann struggled deeply with depression, and he took his own life in 1906.
Wow. That is heavy.
It is, especially because just a few years later, experiments finally proved the definitive existence of atoms, totally vindicating his life's work.
His legacy basically built modern physics.
It did. It's the bedrock. But the story doesn't stay in the realm of physics. It takes a very sharp turn in the 20th century. We leave the steam engines, we leave the gas atoms, and we enter the digital age.
Okay, so this is the part of the source material that always confuses me. We start talking about computers and phone lines, and suddenly the word entropy shows up again out of nowhere.
It does.
Is it the exact same entropy? Or are they just reusing the word?
It is the exact same fundamental concept. And the man who made that brilliant connection was Claude Shannon.
The father of information theory.
Yes. So picture this. It's 1948. Shannon is working at Bell Labs. He isn't worried about coal or steam or hot gas. He is worried about telephone wires.
Communications.
Right. He wants to solve a very specific engineering problem. How much information can I shove down a noisy telephone wire without the message getting garbled by static?
So he's trying to measure information, but how do you actually measure that? You can't put a conversation on a scale and weigh it.
That was his stroke of genius. He realized that information isn't a physical substance. It is fundamentally about the resolution of uncertainty.
Okay, walk me through that.
Sure.
Resolution of uncertainty.
Let's go back to our gambling analogies. A coin toss. Imagine I have a two-headed coin. It's a trick coin from a magic shop. Both sides are exactly the same.
Okay.
I hold it up. I am about to flip it. How uncertain are you about the result?
0. I know for a fact it's going to land on heads.
So when I flip it and I look at it and I tell you, hey, it's heads, did I give you any new information?
No. I already knew it was going to happen.
Exactly. 0 uncertainty means 0 information was gained. That system has 0 entropy. Now, take a normal, fair coin, 50-50 chance. I'm about to flip it. Are you uncertain?
Yes. It could be heads or tails. I don't know.
So when I flip it and I tell you it's heads, I have now resolved your uncertainty. I have given you exactly 1 bit of information.
So a bit isn't just a term computer programmers use. It's a literal measure of surprise.
Yes. Shannon defined entropy as a measure of the surprise or unpredictability of a message. If a message is totally predictable, like if I just send you the letter A 1,000 times in a row, it has very low entropy. You don't need many bits to compress or describe it.
But if it's random.
If a message is totally random and unpredictable, it has maximum entropy. You need the absolute maximum number of bits to describe it because every single letter is a surprise.
But wait, hold on. This is where my brain starts to itch a little. Boltzmann talked about physical atoms and physical heat. Shannon is talking about coins and phone lines and data. Why are we using the same word? Did Shannon just steal it because it sounded cool?
There is actually a famous anecdote about that. The legendary mathematician John von Neumann allegedly told Shannon to use the word entropy for his theory because, quote, nobody knows what entropy really is, so in a debate, you will always have the advantage.
That is fantastic advice. I'm definitely going to use that in my next argument.
It's hilarious, but jokes aside, the connection is mathematically precise. And it was solidified a few years later by a physicist named E.T. Jaynes.
How did Jaynes connect the physical atoms to the digital data?
Think back to our gas in the box. We know the temperature. That's the macrostate. But we don't know the exact position of every single atom. That's the microstate.
Right. We have uncertainty about the atoms.
Jaynes argued that thermodynamic entropy, the heat stuff, is actually just a specific physical case of Shannon entropy. The entropy of the gas is literally a measure of the missing information we have about the system.
Whoa. Slow down. So entropy isn't a physical substance. It's not some slime that builds up in an engine. It's just a measure of my own ignorance.
In this framework, yes. Imagine you were a magical demon who could see and track the exact position and velocity of every single atom in the entire universe.
Okay, an all-knowing demon?
To that demon, there is no missing information, so the entropy would be zero relative to them. But because we mere humans can only see the blurry averages, the temperature, the pressure, the entropy quantifies exactly how much information is hidden from us down in those microstates.
That is a profound shift in perspective. It takes entropy from being a property of the stuff itself to being a property of our knowledge about the stuff.
Yes, entropy is what we don't know. And this definition turns out to be the master key. It unlocks everything else. It unlocks biology. It unlocks black holes, all of it.
Well, let's use that key to unlock biology then, because this brings us to part 2 of our discussion, the active debate, where science disagrees. And this is where the war against decay really starts.
It is.
If the second law strictly says everything tends toward disorder and everything tends toward a bland equilibrium, what about us?
Right. Look at a giant redwood tree. Look at a human body. Look at the complex machinery of a single cell. Are we disordered?
No. We are incredibly specific. We are highly, highly organized. A random pile of carbon and water atoms doesn't just accidentally shuffle itself into a human brain. That seems like an incredibly low probability state.
Extremely low probability. So the big question is, are we breaking the law? Are living things entropy outlaws?
That was the exact question Erwin Schrödinger asked, wasn't it? The same guy with the quantum cat.
The very same. In 1944, he wrote a tiny but massively influential book called What is Life? It is easily one of the most important science books ever written. He looked at biology strictly through the lens of quantum physics and thermodynamics and basically said, this doesn't make sense.
The universe wants to turn everything into static dust. But life somehow builds these magnificent cathedrals of complexity.
Exactly.
And he proposed that life feeds on something he called negative entropy, right?
Yes, or negentropy for short. He said organisms literally suck orderliness from their environment. It's a very striking image. We eat food, which is highly ordered, low entropy chemical energy, and we use that order to build and maintain our bodies.
But I gathered from the research notes that negentropy isn't really a term modern physicists like to use anymore. It sounds a bit mystical, like a sci-fi energy field.
It does sound like magic. And Schrödinger actually corrected himself later on. He admitted he was really talking about free energy, specifically what chemists call Gibbs free energy. Think of it like a battery charge.
Okay, so we eat charged batteries, like an apple, and we discard dead batteries, like waste.
Basically. But the real key to resolving the paradox, the reason life doesn't actually violate the second law, is that we are open systems.
We aren't a closed box.
Exactly. The second law only says entropy must inevitably increase in a completely closed, isolated system. But Earth isn't closed. Earth gets a massive, continuous bath of low entropy energy from the sun every single day.
And we radiate our messy heat back out into dark space.
Think of the refrigerator sitting in your kitchen right now. Inside the fridge, it is cold and ordered. It has actively reversed the natural flow of heat. It created a low entropy pocket. Does your fridge violate the laws of physics?
No, because it's plugged into the wall. It's using electricity. And if you feel the coils on the back of the fridge, they are hot.
Precisely. The fridge reduces entropy locally inside the box by pumping heat out and increasing entropy globally in your kitchen.
So living things are just walking refrigerators.
In a strict thermodynamic sense, yes. We maintain our fragile internal order by continuously exporting high-entropy waste heat, carbon dioxide, scrambled matter out into our environment. We essentially pay for our complex life with the currency of disorder radiated out into the world.
That is a very humbling thought. We aren't transcending physics. We are basically just entropy-generating machines. We actively accelerate the decay of the universe just to keep our own hearts beating for a few decades.
We are surfing the wave of decay. And this brings up a really interesting ongoing debate in the field right now.
The menagerie of entropies.
Yes, because we are now applying this powerful mathematical concept to so many wildly different fields. Ecology, economics, biology, computer science. Scientists sometimes end up talking past each other. They call it the ontological particle problem.
Meaning what exactly?
Well, in traditional physics, the fundamental particle you're counting is an atom. In ecology, the particle you're counting is a whole biological species. In economics, it might be a dollar bill. If you use Boltzmann's famous formula, S equals K log W, but your W counts totally different things, are you really measuring the same underlying reality?
Is it a universal law of nature, or is it just a really useful metaphor we're stretching too far?
Most physicists would argue the math absolutely holds up because it's all just fundamental probability. But there is a fierce disagreement on the ultimate goal of life within this framework.
What do you mean by the goal of life?
Does a complex system actively try to produce entropy as fast as physically possible? That's called the maximum entropy production principle, or MEPP.
So the motto would be burn bright, die young.
Exactly, like a fire finding a sudden draft of oxygen. It wants to consume the available fuel as fast as possible to degrade the energy gradient. Some ecologists argue that dense forests and ecosystems evolved specifically to do exactly this, to maximize the degradation of solar energy.
But then there's the complete opposite view.
Minimum entropy production, MINE-AP. This view, which was championed by Nobel laureate Ilya Prigogine, says that as systems get more complex and mature, they learn to be highly efficient. They try to waste less energy. They try to stay alive longer by delicately sipping the available energy rather than aggressively gulping it.
So is nature a glutton or a miser? Which one is right?
It seems to be a complex trade-off. When resources are incredibly abundant, like intense sunlight hitting a young jungle nature maximizes production. But when resources are scarce, it optimizes for extreme efficiency. It's highly context-dependent.
Before we leave biology and the physical Earth, we absolutely have to talk about one more thing that bridges us to the truly weird stuff.
Oh, Landauer's principle?
Yes, Rolf Landauer. This blew my mind.
IBM, 1961. Landauer asked a profoundly strange question. Does thinking actually cost energy? Does the pure logical act of processing information physically heat up the physical world?
See, I always just assume my laptop gets hot because of physical electrical resistance in the copper wires.
Yeah.
Like friction.
That is true for the inefficiency of our current hardware. But Landauer found something much deeper and more fundamental. He mathematically proved that the purely logical act of erasing information, resetting a digital bit from a 1 to a 0, has a fundamental, unavoidable thermodynamic cost.
You literally cannot erase information without burning energy.
You cannot. To lower the entropy of that specific bit by forcing it back to a known 0 state, you must release a specific calculated amount of heat into the surrounding universe.
The phrase in the notes was, forgetting is a thermodynamic process.
It perfectly ties Shannon and Boltzmann together. Information is physical. A memory stored in your biological brain, a text file saved on your silicon hard drive. These aren't just abstract magical ghosts. They are specific physical arrangements of matter that require energy to maintain and manipulate. And when you finally destroy them, the universe demands a strict heat tax.
And if information is physical, if it's deeply tied to matter and energy, then we have a huge universe-breaking problem when things disappear completely.
We do. Which brings us to the monsters lurking in the dark.
Part 3. Frontiers. Black holes.
Yeah.
The ultimate cosmic trash compactors.
This is the absolute edge of modern physics. This is where our classical understanding of entropy violently breaks down and then has to rebuild itself into something completely mind-blowing.
Okay, establish the core conflict for me. Why exactly were black holes a problem for the concept of entropy?
Well, in the mid-20th century, the classical view from general relativity was that black holes were actually very, very simple objects. The physicist, John Wheeler, famously coined the phrase, black holes have no hair.
No hair, meaning what?
Meaning they have no complex distinguishing features, no bumps, no ridges, no mountains, no internal structure that we can see. If you know just 3 basic numbers, the mass, the spin, and the charge, you know literally everything there is to know about that specific black hole.
So if they're perfectly smooth and perfectly simple, that sounds like a single unique state. A single microstate.
Exactly. One possible configuration, a perfectly smooth sphere of gravity. Which means, going back to Boltzmann's formula, W equals 1 and the log of 1 is 0.
Which means entropy equals 0. A black hole has absolutely 0 entropy. Okay, I follow the logic.
But here's the catastrophic problem. Imagine I have an enormous library full of millions of books. Highly ordered, incredibly high entropy because of all the detailed information inside.
Yeah.
I take that massive library and I throw the whole thing straight into a black hole.
The books disappear past the event horizon. They're gone forever.
The black hole swallows them. It gets a tiny bit heavier because of the mass, but it is still fundamentally hairless. It still has 0 entropy. So where did the immense entropy of the library go?
I see the problem. If the library had massive entropy and the black hole has 0, the total entropy of the entire universe just went down. I just permanently scrub disorder from the cosmos.
And that completely violates the second law of thermodynamics. You cannot decrease the total entropy of the universe. So the physics community had a massive crisis. Either the second law is wrong, and if it is, all of modern physics crumbles, or black holes somehow do have entropy.
And enter Jacob Bekenstein.
A graduate student, of all people. Bekenstein looked at this immense paradox and simply said, the black hole must have entropy. It has to. And he realized that when you throw something massive into a black hole, the black hole gets physically bigger. Its event horizon, the dark surface of the sphere, actually expands.
So he linked the hidden entropy to the physical size of the hole.
Yes. But here is the massive kicker. Here is what shocked everyone. Usually, if I want to know how much stuff, how much information fits inside a box, I measure the volume of the box. 3D space.
Right. A bigger box holds more gas, more books, more stuff.
Yeah.
Entropy naturally scales with volume.
Bekenstein found that for a black hole, the math showed entropy doesn't scale with volume at all. It scales with surface area, the 2D area of the event horizon sphere.
Wait, why is that so weird?
Imagine you're trying to fill that library with books. Usually the number of books you can fit depends on the empty 3D space inside the room. Bekenstein was mathematically saying that for a black hole, the amount of information it holds is determined by how many square inches are on the walls. Like you are perfectly plastering the books onto the 2D wallpaper, not stacking them in the center of the room.
That suggests the inside the black hole doesn't even matter.
It suggests the total information of everything that ever fell in is somehow encoded or smeared onto the two-dimensional surface of the event horizon.
That is completely bizarre.
It gets even better. Stephen Hawking enters the chat. He initially hated Bekenstein's surface area idea. He thought it was ridiculous, and he actively tried to disprove it. But when Hawking sat down and did the rigorous math using quantum field theory, he found something completely shocking.
Hawking radiation.
Yes. He found that black holes aren't truly 100% black. They actually glow. They emit a very faint thermal radiation. And because they emit heat, they must, by definition, have a temperature. And if they have a temperature, they absolutely must have entropy. Hawking definitively confirmed Bekenstein's wild idea, even though he set out to destroy it.
So black holes they're slowly evaporating.
Yes, incredibly, unimaginably slowly, but yes. They are thermodynamic objects. They are giant cosmic entropy buckets. In fact, if you sit down and calculate the cosmic entropy budget for the entire universe, supermassive black holes account for almost all the entropy that exists.
Really? More than all the burning stars?
Yeah. A single supermassive black hole in the center of a galaxy contains vastly more entropy than all the stars, all the gas, and all the dust in the entire visible universe combined. We are literally just tiny, low-entropy dust motes floating in a vast universe dominated by these invisible entropy giants.
That is staggering. But let's go back to that surface area thing for a second. If the total information of a 3D object, like the massive star that collapsed to form the hole, is entirely stored on a 2D surface, the horizon.
You are anticipating the holographic principle.
This is the part of the research that legitimately keeps me up at night.
It should. Physicists like Leonard Susskind and Gerard Hooft took Bekenstein and Hawking's math and ran with it. If a black hole can perfectly store 3D information on a 2D surface without losing anything, maybe the whole universe works that exact same way.
Maybe we are just a projection.
It is mathematically possible that our entire 3D reality, you, me, the room we're sitting in, this microphone, is mathematically equivalent to a 2D field of quantum data encoded on a distant, flat cosmological horizon. We might literally be a holographic projection.
So, trying to make Victorian steam engines a little bit more efficient eventually led us to question whether physical reality even has depth.
That is the raw power of this concept. Entropy is the thread that pulls on the very fabric of reality until it unravels.
Well, let's pull the thread back down to Earth for part 4, the implications. Because as much as I love a good session of existential cosmic dread, we do have to wake up and live in this society.
We do.
And it turns out entropy applies to our daily lives here too.
It does. Because once you deeply understand entropy, not just as heat loss, but as probability and information uncertainty, you can apply that mathematical framework to almost any complex system.
Let's talk about economics.
The Thiel Index. I read about this in the brief. It measures human inequality using entropy math.
Yes, but it completely flips your normal intuition upside down. So, in physical thermodynamics, what is the ultimate state of maximum entropy?
Equilibrium. Everything is mixed perfectly evenly. The hot and cold water merge until everything is the exact same lukewarm temperature.
Right. It's a state of bland, featureless uniformity. Now, translate that exact concept to human income. What would maximum entropy look like for a population's wealth distribution?
I guess. Everyone has the exact same amount of money.
Exactly. Perfect, absolute financial equality is the state of maximum entropy. It is statistically the most random distribution because knowing who a specific person is tells you absolutely zero new information about their income because they are all exactly the same.
That's wild. So in economics, high entropy perfect equality is often seen as a utopian political goal, whereas in physics, high entropy is the heat death and end of the universe.
Context is absolutely key. The Thiel index mathematically measures the entropic distance between our current real-world wealth distribution and that theoretical state of perfect equality.
So a very high Thiel index number means we are far away from entropy.
Yes. A high index means we have low entropy. It means we have high order, which, translated into economic terms, means segregation or extreme concentration of wealth. One billionaire has all the money and everyone else has none. That is a highly ordered, incredibly low probability state.
It's fascinating that order is mathematically associated with extreme inequality. It implies that maintaining inequality actually requires constant energy.
That is the core insight of social entropy theory, which was developed by a sociologist named Kenneth Bailey. He basically argued that human society is a complex structure that constantly fights against natural decay.
It's the messy room problem, but applied to human civilization.
Exactly. Without massive constant inputs of new energy and new information, social structures inevitably fall apart. Roads physically crumble, laws are gradually ignored, institutions fade into irrelevance. Entropy always rises.
And Bailey said money acts as the energy in this societal system.
Money and information, yes. He viewed money as the primary regulatory mechanism, the social metabolism. It actively directs the flow of human work to repair the roads and enforce the laws. If the flow of money stops, the repair work stops, the structure degrades, and social entropy rapidly rises.
It really highlights how fragile civilization actually is. We tend to think of massive cities and ancient governments as solid, permanent things, like rocks. But they're actually just dissipative structures.
Dissipative structures. That's Ilya Prigozhin's concept again. A city is exactly like a candle flame. A flame looks like a solid, persistent object. It has a recognizable shape. You can point to it. But it isn't an object at all. It's a constant, raging flow of gas combustion. If you stop the flow of gas for even a second, the flame vanishes.
And a city is just a massive flow of food, electricity, water, and people.
Sucking in vast amounts of low-entropy resources and constantly excreting high-entropy waste like trash and heat and pollution. A city is just an engine for creating intense local order by ruthlessly exporting chaos out into the countryside and the atmosphere.
Okay, finally, I want to touch on the deeply personal side of this. Psychological entropy. There was this concept in the notes of anxiety as entropy.
This is a relatively newer framework in neuroscience, often called the free energy principle, championed by people like Carl Friston. It views the human brain fundamentally as a prediction machine.
Its main job is just to guess what happens next.
Yes. To survive in a dangerous world, you critically need to know where the predator is hiding. You need to know if that bright red fruit is poisonous. So your brain constantly builds and refines an internal statistical model of the outside world.
So where does the concept of entropy come in?
In this model, entropy is simply the mismatch between your brain's prediction and actual reality. It is the mathematical measure of surprise. If you walk into your safe, familiar house and there is suddenly a live tiger sitting on your sofa.
Massive surprise, extremely high entropy.
And how does that mathematically high entropy feel to you emotionally?
Pure panic, severe anxiety, terror.
Exactly. High psychological entropy is consciously experienced by us as anxiety. It is the deeply uncomfortable feeling of, I don't know what is happening, my model is failing.
So we actively build daily routines to manually lower our entropy.
Yes. We check our phones constantly, we follow rigid daily schedules, we stay safely inside our comfort zones. All of these seemingly mundane behaviors are actually designed to minimize the surprise of our sensory inputs. We are constantly, desperately trying to flatten the entropy curve of our own lives.
So my absolute obsession with checking my email inbox isn't just a bad modern habit. It's literally a thermodynamic imperative to reduce uncertainty in my environment.
You are trying to resolve the uncertain bits of information. You are trying to reach a calm, zero entropy state of absolute knowing. It's physics driving psychology.
Wow. We have covered an absolutely incredible amount of ground today.
We really have.
We started in the thick, cold-choked smog of the Victorian era with Clausius. realizing that you just can't get something for nothing, that nature strictly charges a heat tax on every single transformation.
And then we sat with Boltzmann and his deck of cards, realizing that chaos isn't some malicious force of evil, but just a cold, statistical inevitability. Messy just means highly probable.
We watched Claude Shannon completely redefine entropy into digital bits of surprise, and E.T. Janes reveal that entropy is really just a mathematical measure of our own human ignorance.
We saw fragile biological life fighting the cosmic tide, acting as giant biological refrigerators to stay organized in a decaying universe. And we saw Landauer mathematically prove that forgetting is a physical act of burning energy.
And finally, we stared straight into the dark abyss of the black hole, where the 3D information of the universe might just be plastered onto a 2D wall, hinting that our entire reality is a hologram.
It profoundly changes how you see the world, doesn't it? It's not just a depressing story about things eventually falling apart. It's actually about the constant, noble, beautiful struggle to create and maintain meaning, to boldly keep the signal clear against the overwhelming background noise of the universe.
I keep thinking about Landauer. If erasing information literally creates heat, if forgetting is a physical slide toward ultimate disorder,
Then remembering is a physical act of defiance.
exactly, the act of preserving knowledge, like exactly what we're doing right here, researching these complex topics, sharing these stories, archiving this digital audio, it is quite literally a form of thermodynamic resistance.
It really is. We are actively fighting the inevitable heat death of the universe, one deep exploration at a time.
That feels like a truly worthy mission.
Before we wrap up, thank you to all our partners, sponsors, and scholars who made this podcast and the research possible. We're truly grateful for your support.
And to our listeners, thank you for being part of this journey with us. Hope you enjoyed today's discussion. If you did, be sure to subscribe and support us in Patreon. And of course, you can write to us in comments if a specific topic needed to be covered, which help us all to grow.
Until next time, stay curious, keep learning, and let the search for wisdom guide you forward. Have a great day.